Reflection of light. When light falls on a highly polished surface like a mirror, most of the light is sent back into the same medium. This phenomenon is called reflection of light. Laws of reflection. The laws of reflection state that the angle of incidence is equal to the angle of reflection, and the incident ray, the normal to the mirror at the point of incidence, and the reflected ray all lie in the same plane. Spherical mirror. Look at the sphere. Now cut out a spherical mirror from the sphere. You see that center? This center of sphere is called the center of curvature. Thus the center of curvature is defined as the center of a sphere from which the given spherical mirror, concave or convex mirror, is obtained. Pole. The center of the reflecting surface of a spherical mirror is called the pole. It is represented by capital P. Radius of curvature. The radius of the sphere is called the radius of curvature. It is represented by capital R. Principal axis. The line joining the pole and the center of curvature is called the principal axis. Let us do an activity for focus. Take a concave mirror and place it in sunlight in such a manner that the reflecting surface should be towards the sunlight. Now, place a small sheet of paper at the center of curvature. Now move the sheet towards the pole of the mirror. Do you see anything on the paper? Yes. A bright intense spot is formed on the paper. Why does it happen? The light rays falls on the mirror and after reflecting, it converts at a single point. This single point is the focus of the mirror. The focus is the point on the principal axis on which the light rays parallel to principal axis meet or appear to diverge from after reflection. Principal focus. In mirrors with small apertures or diameters, roughly half of the radius of curvature is equal to the focus point. Spherical mirrors are of two types: concave mirror and convex mirror. Concave mirror. Concave mirror is a spherical mirror whose reflecting surface is curved inwards. Rays of light parallel to the principal axis after reflection from a concave mirror meet at a point or converge on the principal axis. Convex mirror. Convex mirror is a spherical mirror whose reflecting surface is curved outwards. Rays of light parallel to the principal axis after reflection from a convex mirror get diverged and appear to come from a point behind the mirror. Image formation by a concave mirror. Click on the button of the position of objects to see the ray diagram of image formation, nature of image, and size of image. Uses of concave mirrors. Concave mirrors are used in torches, searchlights, and headlights of vehicles to get parallel beams of light. They are also used as shaving mirrors to see larger image of the face. They are used by dentists to see larger images of the teeth. Large concave mirrors are used to concentrate sunlight to produce heat in the solar furnaces. Image formation by a convex mirror. If an object is placed between infinite and the pole of mirror, the rays which are parallel to the principal axis after reflection seem to appear at the focus. Another ray which strikes the pole is reflected at an equal angle with the principal axis. If the two rays intersect with each other, then an image is formed at the intersecting point. The image is virtual, erect, diminished, and between P and F. If the object is placed at infinite, image is formed at the focus, highly diminished, virtual, and erect behind the mirror, point-sized. Convex mirrors are used as rear-view mirrors in vehicles. Convex mirrors give erect, diminished images of the objects. They also have a wider field of view than the plane mirrors. Images formed by convex lens. When the object is at infinity, the image is formed at the focus f2. It is highly diminished, real and inverted. When the object is beyond 2f1, the image is formed between f2 and 2f2. It is diminished, real and inverted. When the object is at 2f1, the image is formed at 2f2. It is the same size as the object, real and inverted. When the object is between 2f1 and f1, the image is formed beyond 2f2. It is enlarged, real and inverted. When the object is at f1, the image is formed at infinity. It is highly enlarged, real and inverted. When the object is between f1 and O, the image is formed on the same side of the lens. It is enlarged, virtual and erect. Refraction. When light travels obliquely from one transparent medium into another, it gets bent. This bending of light is called refraction of light. For example, when we put a pencil in a glass, we can see it clearly. But when poured in water, we see the pencil bent due to the refraction of light. When light travels from a rarer medium to a denser medium, it bends towards the normal. When light travels from a denser medium to a rarer medium, it bends away from the normal. The incident ray, the refracted ray, and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. The ratio of sine of angle of incidence to the sine of angle of the refraction is a constant for the light of a given color and for the given pair of media. This law is also known as Snell's law of refraction. Sin I by sin R is equal to constant. The absolute refractive index of a medium is the ratio of speed of light in air or vacuum to the speed of light in medium. The relative refractive index of a medium 2 with respect to a medium 1 is the ratio of the speed of the light in medium 1 to the speed of light in medium 2. Refraction of light to a rectangular glass slab. Let us explain the refraction phenomenon by a glass rectangular slab. Fix a sheet of white paper on a drawing board using drawing pins. Place a rectangular glass slab over the sheet in the middle. Draw the outline of the slab with the pencil. Let us name the outline as ABCD. Take 4 identical pins. Fix 2 pins, say E and F, vertically such that the line joining the pins is inclined to the edge AB. Look for the images of the pins E and F through the opposite edge. Fix 2 other pins, say G and H, such that these pins and the images of E and F lie on a straight line. Remove the pins and the slab. Join the position of tip of the pins E and F and produce the line up to AB. Let EF meet AB at O. Similarly, join the positions of tip of the pins G and H and produce it up to the edge CD. Let HG meet CD at O. Join O and O. Also produce EF up to P as shown by a dotted line. From this activity, when a ray of light passes through a rectangular glass slab, it gets bent twice at the air-glass interface and at the glass-air interface. The emergent ray is parallel to the incident ray and is displaced through a distance. Spherical lenses. A spherical lens is a transparent material bounded by two surfaces, one or both of which are spherical. Spherical lenses are of two types. They are convex and concave lenses. Convex lens is thicker in the middle and thinner at the edges. Rays of light parallel to the principal axis after refraction through a convex lens meet at a point or converge on the principal axis. Concave lens. Concave lens is thinner in the middle and thicker at the edges. Rays of light parallel to the principal axis after refraction get diverged and appear to come from a point on the principal axis on the same side of the lens. Rules of image formation. In a convex lens, a ray of light parallel to the principal axis after refraction passes through the focus on the other side of the lens. In a concave lens, it appears to diverge from the focus on the same side of the lens. In a convex lens, a ray of light passing through the focus after refraction goes parallel to the principal axis. In a concave lens, a ray of light directed towards the focus after refraction goes parallel to the principal axis. In a convex lens and a concave lens, a ray of light passing through the optical center goes without any deviation. Images formed by convex lens. When the object is at infinity, the image is formed at the focus f2. It is highly diminished, real and inverted. When the object is beyond 2f1, the image is formed between f2 and 2f2. It is diminished, real and inverted. When the object is at 2f1, the image is formed at 2f2. It is the same size as the object, real and inverted. When the object is between 2f1 and f1, the image is formed beyond 2f2. It is enlarged, real and inverted. When the object is at f1, the image is formed at infinity. It is highly enlarged, real and inverted. When the object is between f1 and O, the image is formed on the same side of the lens. It is enlarged, virtual and erect. Images formed by concave lens. When the object is at infinity, the image is formed at the focus f1 on the same side of the lens. It is highly diminished, virtual and erect. When the object is between infinity and f1, the image is formed between f1 and O on the same side of the lens. It is diminished, virtual and erect. Sign convention for spherical lenses. The sign convention for spherical lenses is the same as in spherical mirrors, except that the distances are measured from the optical center, O. The focal length of a convex lens is positive and the focal length of a concave lens is negative. The lens formula for spherical lenses is the relationship between the object distance, u, image distance, v, and the focal length, f. The lens formula is expressed as magnification for spherical lens is the ratio of the height of the image to the height of the object. The magnification is also related to the object distance and image distance. It can be expressed as power of a lens. The power of a lens is the reciprocal of its focal length in meters. The SI unit of power is diopter. 1 diopter is the power of a lens whose focal length is 1 meter. The power of a convex lens is positive and the power of a concave lens is negative. The object is always placed on the left of the mirror and the object falls from left to the right. All distances parallel to the principal axis are measured from the pole. All distances measured to the right of the pole are taken as positive. All distances measured to the left of the pole are taken as negative. The height measured upwards perpendicular to the principal axis is taken as positive. The height measured downwards perpendicular to the principal axis is taken as negative. The mirror formula for spherical mirrors is the relationship between the object distance, u, image distance, v, and the focal length, f. Magnification of spherical mirrors is the ratio of the height of the image to the height of the object. The magnification is also related to the object distance and image distance. It is expressed as h2 by h1 or equal to V by minus U. Image formed by concave mirror. Let us do an activity to better understand the image formation by concave mirror. Place a candle in front of a white sheet and put the candle in such a way that it is far off the concave mirror. What do you observe? Now start moving the candle towards the mirror and place the candle very close to the concave mirror. What do you observe? At the end of this activity, we can conclude concave mirror forms real, inverted and diminished image when object is placed far off the mirror. Concave mirror forms a real, inverted and highly magnified image when the object is placed nearer to it. Concave mirror forms a virtual, erect and highly magnified image when the object is placed very close to the concave mirror. Representation of images formed by spherical mirrors using ray diagrams. Let us see the rule to draw a ray diagram of a spherical mirror. A ray parallel to the principal axis after reflection will pass through the principal focus in case of a concave mirror or appear to diverge from the principal focus in case of a convex mirror. A ray passing through the principal focus of a concave mirror or a ray which is directed towards the principal focus of a convex mirror after reflection will emerge parallel to the principal axis. A ray passing through the center of curvature of a concave mirror or directed in the direction of the center of curvature of a convex mirror after reflection is reflected back along the same path. A ray incident obliquely to the principal axis towards a point P or pole of the mirror on the concave mirror or a convex mirror is reflected obliquely. The incident and reflected rays follow the laws of reflection at the point of incidence or point P, making equal angles with the principal axis.